Okay, so for the next section, again, we are approaching this lesson as if you had time to go home and try some questions, right? But ultimately, the main point would be to be able to look at a coordinate, tell me what your x is, tell me what your y is. Also, look at a graph, tell me what independent is, tell me what dependent is. And essentially, it's testing whether you have the ability to use a system, right? To use an x and a y. If you haven't gotten a sheet yet, come grab one. This is the next bit. Oh, that's a lot of noise. Okay, go for it. Okay, all right. So again, our first lesson on Cartesian coordinates was just to get a sense of the system, how to read the system, how to use the system. And we apply it to science where, hey, if this changes, how does that change this? If this changes, how does it change that? It was always a relationship between x and y. And you know what? In science, typically speaking, that's as far as we care. We want to see the relationship so we can say, oh, let's go to the next experiment. Let's go, let's go, let's go. You can think about it as a little bit of, you can think of science as being more impatient, right? We found the relationship. Okay, let's figure out what the next thing we can do too. We can establish some more truths in health or whatever. In math, we are equally as interested in identifying the trend as well as actually identifying the number, the answer. So in math class, you need to be able to do both. In science, I just want the trend. I want you to talk to me about it. I want you to convey and to communicate and argue with me the trend. In math, not only do you have to know the trend, but you have to start answering with numbers. So let's talk about that first part first, the trend, or otherwise known as the rate of change. Rate being like how quickly something is changing. Okay? Basics. I have 3 graphs for you in the first page. And I ask you, is there a trend? If so, please describe it using the method that we did before. Just simply like positive or negative correlation is fine. Popcorn sales. Well, the title says a lot, but I can assume a lot too. So let's take a look at what they are comparing. Price, number sold. Here is a scatter plot with a bunch of random data. What can you tell me about the relationship between these 2 variables? One?
When the price is more expensive, the number of sold is less.
Right. So as price increases, number sold decreases. That would be what we call a, so let's do it this way, negative correlation, right? In a simple way, you can say a negative correlation is when a relationship shows a downward trend. Do you see how I'm using that word? I'm going to be throwing the word trend out a lot, so I need you to be very comfortable with it. Okay? There is you're tending to go lower and lower as we progress, as we go along this journey. So this is a negative correlation. It is you can also call it a downward trend. It's getting closer and closer to negative, right? It's going down. Is there any other ways I can, oh, you can also, instead of saying a negative correlation, you could say it is a negative rate of change. What do I mean by that? If I increase the price, Does it change in the positive direction or does it change in the negative direction? That's what I'm asking. As I continue to go to the right, I'm going down. If I move to the right, I'm going down. If I move again to the right, I have to go down. If I'm moving to the right, I have a downward staircase. I don't know how many different ways I could explain it to you, but do you get my point? Do you see why we would call this a negative trend or a negative rate of change or a downward trend, correlation, so on and so forth? I hope so. I'm not going to spend too much time in the next one. What about the next example? Someone want to take a big risk and tell me a little bit about the next scatter plot. Huh? There you go. Why? Sure. You could also say, hey, there's an upward staircase. Sure. Right? There's so many different ways you could say. I'll just call it a positive correlation and just leave it at that. I don't think I have to go any further. Which brings me to a very interesting case for number 3. Age and shoe size of students in Miss Ochoa's class. I don't even know how to pronounce that. Okay. Age of student, shoe size. Do you see a relationship? There could be, if there was more data, who knows, right? But as far as I can see, there is no correlation. But you could technically say no trend, but in terms of rate of change, I want to give it a number. What is a number that typically represents nothing? So you can say there's a 0 rate of change. Why do I say that? This might make sense to some of you who are a little bit more number inclined, who don't mind numbers too much. This might make sense when we start doing some math, the word 0. Okay? And it's the idea that I can't draw a line going upwards. I can't draw a line going downwards. In fact, the best line I could probably draw is a line going perfectly horizontal because I don't know. There's no change. It doesn't go up, doesn't go down. It's just stays the same. There's no real relationship between the two. Okay. So I sort of merged my first exercise with the key idea, and the idea is this. If the rate of change, how quickly I'm going up or down, is positive, negative, or 0, you can identify it in a variety of ways. You could identify it graphically. You could identify it using data, with a scatter plot, with a line. There's so many different ways. Okay. So by definition, put a highlighter for this one. This correlation, the rate of change that describes is a rate that describes how the dependent variable changes as I increase or as I change the independent variable. So there's a reason why I'm trying to force the staircase on you. It makes a lot of sense. If I start here, if I change the x variable by 1, am I going up? Yeah. I'm right here. If I say the x variable is a 2, I have to go up. So every time I change the x variable, my y variable also happens to increase, and so we say it's positive. Take a look at this one. If I move my x to the right, if I move 1, what happened to the y? It went down. If I moved it once, the y went down. If I moved it again, my y is going down. And so the y value is decreasing. The y value is decreasing. And so negative rate of change. So you can say y value is increasing. Here, y value is decreasing. And I said before, the y value is neither increasing nor decreasing. The rate of change is 0. So let's talk. So this is the aspect where I said math is more interested in numbers and not just describing a trend. Example, please take a look at the graph on the right. The graph on the right shows Greta's distance from home in meters for the first 10 minutes of her evening walk. Is Greta moving towards the home, or towards home, or away from home? Explain. Context, everyone. Context. The graph shows Greta's distance from home. So when I begin, how far away is she from home? 0. Okay, she's 0 meters away from home. Think about what that means. 10 minutes after, she is 900 meters away from home. Is she moving towards home or away from home? Yeah, right? Away, right? Because distance from home is increasing. Right. Here's another scatter plot-like question you can see in the future. How far from home is Greta after 6 minutes? What do they want? What do they give you? Between X and Y. Think about this like it was an algebra question. What do they want? X or Y. And what do they give you? X or Y. Did I pick on someone? Marshall, you with me? Yeah. What do they give you? You have a 50-50 chance. Is that X or is that Y? It is. They give you X and they're saying X is 6, right? Because that's independent. So what are they asking for then? Right, which is represented by Y. So they're asking, what's Y if X is 6? That's what it means mathematically. But you have to translate it into math. If X is 6, where's the Y? Da, 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 da. That means Y must be, right? If X is 6, the Y value is 540. And so, how far from home is Greta? Greta is 540 meters away. You have to make that connection. Some of you, it's like, duh, obvious. Other people will need to process this. And again, work on the speed in getting there. Is Greta increasing her speed, reducing her speed, or maintaining a constant speed? Explain. So here's a question that slightly dabbles into the physics aspect. And some people will see it, other people will need an explanation. First, someone tell me what they think is the answer. Is Greta getting faster? Is Greta slowing down? Or are they maintaining a constant speed? Elliot?
I think it's staying the same.
Correct. You're right.
Because if you look at 1 minute is 90 meters, and then you look at 2 minutes is 180. 180 is exactly double of 90.
Right. So you can say every staircase or every step of the way, how much am I adding? Yeah, plus 90, plus 90, plus 90, plus 90, plus 90. And I'm doing that 10 times, right? It's literally 90 times 10, that same number, right? So how about I write it? Every minute that passes exactly 90 meters is traveled, right? So you can say it's constant, it doesn't change. Shameless plug. If I asked you for the unit rate for the speed, what would you say? Yeah. Yeah. Every minute, right? So it's 90 meters per minute. 90 over 1. It's all coming together, right? Do you see why I was being all annoying with you since February? It's all coming together. Okay, we're getting there. This is like a really important part of the math world. So here we go. What unit would be used to describe the rate of change? Oh, I jumped the gun. What did I describe right here? Right? How much I'm changing every x. That's my rate of change. What unit would be used to describe the rate of change? I am changing, so basically, so in words, I would say how much y is changing, right? Over how much x is changing. Can you even read that? Is that really messy? I think so. Yeah, let me rewrite that a little bit. So what you're essentially doing is this. How much does the y change over how much does the x change? Would that make sense? That's what the staircase is, right? I asked you, every time I travel for 1 minute, how does that affect my y? It was 90 minutes, sorry, 90 meters per minute. It's meters per minute. So what unit? Well, it's meters per minute. Not everyone uses meters per minute. Typically, when you're talking about how much you travel per time in a car, we use speed, which is, yeah, kilometers per hour, right? But anyways, I think you get the point. Is the rate of change positive or negative? Well, I'm going to say positive. Why? Again, I think my answer would be as x increases, y increases, right? And that's the most important part. They're both increasing together. Another way you can describe it is, as I continue on along the graph, I am adding a value every single time. So it's positive. Is there another way you might describe it? Are you looking at this slightly differently? How would you interpret a graph like this? This is where your creative juices can work. How about limits? Can you talk about this in terms of limits? If I went x approaches infinity, what is the limit of this graph? If x was 1 million, what's the typical end game for the y value? Where am I going? Yep. So as a limit, you can see that y is going to approach, the y value is going to approach infinity as well. That's one way you can tell that it's a positive rate of change. There's so many ways you can describe it. Okay, let's finish this. F and G. How would the graph look different if Greta was moving in the opposite direction? In other words, let's pretend Greta was 900 meters away. Again, I'm moving in the opposite direction. It's not a trick question. What if Greta started 90 meters away or 900 meters away, and we're walking in the opposite direction to this? I'm getting closer and closer to home, right? So If I'm getting closer and closer to home, I would see a downward trend, aka a negative rate of change. So our graph would show a negative rate of change. Right? Why? Distance to home gets smaller or decreases. And then finish it off, right? So it's, as you can see, as much as it might be math, it's a lot of looking and interpreting and communicating. So part G, what are the independent and dependent variables in this relationship? So let me do this quickly so that I can. What are the independent and dependent variables? Well, independent would be 9 minutes. Dependent would be distance in meters. Okay, last bit. So most of this is just practice questions, but I do want to do one last thing with you, and that is the idea of rate of change to describe, again, a trend, even if it's not a straight line. And this is a concept that grade 12 students do in calculus, but you'll first be introduced to it here so that it's not like a completely thing out of left field when you get to, let's say, physics here. Please go to the next page that says key idea for constant increasing and decreasing rates of change. One last thing, and then you're basically home free, which is a lot of time. Ready? I'm going to give you a scenario where, yes, you see a rate of change, but it's not a straight line. Can you still talk about it though? Here are 3 different scenarios. The rate of change for constant is, as we talked about, consistent. Every single step to the right, I go up by a certain amount, and that amount does not change. Can you say the same for this? Let me give you a description. For the increasing, the little curve here, the one in the middle, if you moved 1 to the right, I go up a tiny little bit. Move 1 to the right, I go up a tiny little bit. But does that tiny little bit stay the same as I move along the graph? What can you tell me about my change? Think about it. Let me reword it. I go to the right, I change by a little bit. I go to the right, positive change by a little bit. Move to the right, my positive change by a little bit. Move to the right, positive change by a little bit. Move to the right, positive change. So for the constant, my change is this little tiny bit. What can you tell me about my change for the middle graph? Use your own words and be wrong. I don't care. What do you think? Tell me what you think. Tell me what you think. You're wrong. Is that okay? That's okay. What can you tell me about how much I'm going up every step of the way? How is it different from my first example? Increasing over time. In a simple way, your rate of change is changing. Does that make sense? How much it's changing is changing. And that's why we have this. Why is stuff like this important? Why is stuff like that is important? In things like finances, like money, do you see the relationship? Wouldn't that be great, right? When it comes to things like medicine, I wonder if you see the relationship. Have I made my little spiel about like Tylenol and stuff like that with you? Did I do that with you? Yeah, well, in science, Madeline might recognize it too. In your body, there are certain mechanisms, and I'm just gonna say, when you get into the health sciences, these kinds of things become so prevalent. And remember, math and science is related to a degree, and then we start branching off. So you need the math, but we really don't have to go too far beyond this level. So if you are interested in the math, in the sciences, and even in the engineering, you'll be surprised at how simple the math is, and then we just explode from there. The foundations are very simple, but what we can use with it is incredible. Let's talk a little bit about how the change is changing with using this example, and then the rest of class, you can try some homework, all right? Example. The graph to the right shows a population of a small town over time. Before we even do the math, does that graph seem realistic to you? Why does the population seem to increase faster and faster and faster and faster and faster? Yeah, okay, so let's just being like imaginary here, okay? Me, Elliot, get it off, okay? And let's assume we're aliens and we're able to have babies. And if that happens, well, these babies will grow up and they will. But that doesn't mean that I only have one child. Right? That's one. So while I'm having more, this alien offspring will suddenly grow bigger and then they will have more children too. So now there's two sources of babies. And there's two sources of babies. Now you get the point. Let's put it this way. Maybe not population. That might be a very bad example. Let's talk about COVID. I think that makes more sense. I have COVID and I cough into Maya's world. Okay? And now she has COVID. Does that mean I don't have COVID? No. Now there's two people spreading. Now I cough into Nolan's mouth. I don't know why I would do that. Okay? Now he's sick, but at the same time, Maya is just as rude and coughs into Eric. Right? Now we have four sources of the sickness. Now I know that I'm healing. That doesn't mean I heal right away. In that same way, if you're talking about the population of viruses, what happened? In a matter of minutes, I went from 1 to 2 to 4. You do the math, that's a plus 400%, well, that's plus 300%. And from 4, what do you think happens? All of us are just as rude then. That's 8. Right? And that 8 becomes 16. And this is why you will see any COVID model, as soon as they start seeing this up to here, the health organization freaks out because they don't want to go from here to here. Same time, isn't it? The first 4 years, this is safe. Or how about the first 4 months? The first 4 months of COVID, this is safe. But if we don't do anything now, the next 4 months are going to be, see how scary that is? That's why people are saying, okay, we need to slow down, we need to mask up, we need to do this and that, even before it seems like it's too bad. It's the reason behind all this, and it's all math. Okay? Let's keep going. Describe how the population is changing over time. What would you say? Don't just say it's increasing. Yep. Oh, now that's a very I'm going to say advanced word when it comes to functions like this. Yes, we are going to talk about exponential graphs. We learned about exponents. How does that apply here? Let's dumb it down a little bit. Can you describe it without using the word exponential? The increase of population is increasing over time. Another way you could say it is the rate of change is changing, the rate of change is increasing. Now that I think about it, in my example, I should have just gone straight to COVID. Yeah, talking to myself. Is the rate of change of the population positive or negative? Positive. And I think that makes sense. That doesn't change from previous, right? We are adding, or the y value increases as x increases. The rate of change is positive. And we're taking a look to see if the y value is increasing or not. That's it. Is the rate of change in this example constant? Once again, taking from part A. The rate of change is not constant. The y value increases more in the next step than it did in the previous step. Does that make sense to people? I'm not sure if I should reword it, so I want to see a bit of a nod or a confirmation. The rate of change is not constant. The y value increases more in the next step than it did in the previous step. Does that make sense? Warren, are you with me? Are you writing anything down? You have to flip a table? Nah. We're good? Identify the dependent variable and the independent variable in this relationship. I hope you can do that. So I hope you understand what I mean by x and y. And then lastly, why do you think a dashed curve was used here instead of a solid curve? Good question. That's not really math, it's just sort of a convention. Think about it while I fill this in. So, why do you think it's more appropriate to draw a dashed curve, aka to predict, not to actually draw a solid line, which suggests exact values? Anyone? I'm gonna wait. Why does it make sense? No math involved. Why does that make logical sense to use dotted lines? Why, right, let's change the question. Why can't you use solid line? Take a guess. Yeah, go ahead, Andy. Well, there is an element of it's nice to do a guided line so that we can follow the trend better. But what is the main reason why I chose, or this person chose, a dotted line instead of actual solid lines, like we did in previous examples? Yeah?
Well, like the solid line will be different each time because the rate of change is changing.
Rate of change is changing. Okay, okay. Sure. I like how you're thinking about it mathematically as well, just like Andy. Let's put it this way. What if it was actually like this? What am I trying to illustrate here? In other words, it's a dotted line because it's a trend. But how is that different from what could be reality? What am I trying to illustrate here if this is a time to population graph? Come on, think about it realistically. The idea is this, everyone. This is the disconnect between mathematics and real life. Mathematics is supposed to model as best as we can what we see in real life. But real life is never perfect. In what world do we have the exact perfect amount of babies every year to create a perfect curve like this? Some years we would have lots of babies, like for example, that's why we call them the baby boomers, right? Sometimes you won't have as many babies because let's say there was a really big recession and people were like, oh, I can't have babies right now, right? On the flip side, let's say on a year like COVID, a lot of people passed away, right? So there might have been a larger dip in the population. And then after COVID, everyone's like, yeah, we're safe. Let's, increase family size, I don't know. And the population shoots back up. Reality is very different from a perfect mathematical model. And so it makes more sense that we predict based on data, a trend. If you drew a dot, a solid line, it would mean that that point actually exists and that is true. A solid line is like a scatter plot right along those lines. And that's actually not true. The dotted line represents a extrapolate, it's a prediction, an interpolation and extrapolation. Okay? So very quickly, I will finish this off and say, dotted line predicts the population, but there is no evidence that those were the actual values in that time of year. Right? Like for example, as I was saying, if the year was here was actually like up and down and then up, right? At year 4 and maybe 2 months, there was a sudden peak in populations. And then maybe some tragedy hit or some kind of huge typhoon or something. And suddenly that's by, I guess the 4th year around September, maybe the population dipped. We don't know, but what we do know is this trend. That's all I'm trying to say when I mention we don't know what the actual values are. Okay. Any questions? Great. And as you can see, for today, it's not as much mathematics as it is looking at a graph and interpreting to the best of your abilities. So I'd like you to practice that. We still have a good 35 minutes before the class ends. What I'm going to ask you to try is any of the stuff that you haven't done yet on the first lesson or the second lesson is yours to do over Wednesday, Thursday, up to Friday. Because the next time I see you is going to be Friday. So these pages from this lesson as well as the previous lesson, please try to do as much of them as possible. It is going to prime you and prepare you really well, especially the vocabulary. It's going to prepare you really well for the next steps that I'm taking. Yes? Tomorrow is Credit Rescue. Thursday is the other OSSL too. So you have your other class, but you don't see it. I'll pause the video here.